Hi friends, today we will discuss an important concept of computer graphics, that is two-dimensional transformations. We all know two-dimensional shapes are circle, triangle, square, rectangle, pentagon, hexagon, heptagon, octagon, nanogon, decagon. These all are represented in two-dimensional shape. And the 3D shapes represented here are sphere, prism, cuboid, cube, cylinder, pyramid, and cone. And two-dimensional transformations. These are transformations, that is, the operations which apply to an object to change its position, orientation, or size are known as geometric transformations. That is, computer graphics provide the facility of viewing object from different angles, enlarge or reduce the scale or shape of an object. And why we are using transformations? It is needed to manipulate the initially created object, what we have initially created, and to display the modified object without having to redraw it. We are applying some transformations on the already created object. And some basic transformations are here: translation, rotation, scaling. Scaling are of two types, uniform scaling and non-uniform scaling, and reflection, shear. And each transformation is a single entity, that is, the object itself is transformed and it is relative to the coordinate system or relative to the background. Only object is moving. Here is translation. Here is this one is the original object, then this is the translated object. Translation moves all points in an object, every points along the same straight line path to a new position. The path is represented by a vector called the translation vector or shift vector. We can write the components as p dash x, translated point, x coordinate, p dash x is equal to original coordinate of px plus some transformation on x-axis, that is tx. Similarly, p dash y is equal to py plus ty. Here in this diagram we are represented p as the coordinates 2, 2, and it is translated to this point, that is p dash of 8, 6. That we are applying a transformation point on x-axis as 6, that is 2 plus 6 is 8, translated to that x coordinate, and for y coordinate ty is 4, that is 2 plus 4, that is 6. Sixth y coordinate is 6. So the translated point is p dash 8, 6. Here we can represent this one translation in a matrix form, that is p dash is equal to p plus t. This one is matrix. Matrix x dash y dash is equal to matrix xy plus matrix tx ty. That is, we can say that translation is the straight line movement of an object from one location to another. Here it is moved from here to origin to this point. Second one is rotation. A rotation repositions all points along a circular path centered at the pivot point. For that, first you have to assume the pivot point is at the origin, like this, and the positive value of the rotation angle rotates an object in anti-clockwise direction. When an object is rotated, then every point of the object is rotated by the same angle. Here we can write the components as p dash x is equal to px cos theta minus py sin theta, and p dash y is equal to px sin theta plus py cos theta. Here theta is represented by this point, this angle. P is original point xy, and p dash is translated point p dash s dash y dash. This one is theta, angle theta. Then here r is the radius, and then this is the x-axis and this is the y-axis. In matrix form, we can write P dash is equal to r into P. For all theta can be clockwise for negative or counterclockwise for positive. Then rotation matrix will be r is equal to matrix cos theta minus sin theta, cos theta. And next one is scaling. Scaling changes the size of an object, and it involves two scaling factors, Sx for x-axis and Sy for y-axis, y-coordinate. Scales are always about the origin. Then we can write the component as P dash x is equal to Sx into Px, P dash y is equal to Sy into Py. That is, scaling is used to alter or change the size of an object. To change the size of an object. Here it is minimized. Here it is changed, altered the size. And the change is done by using scaling factors Sx and Sy. In matrix format, we can write P dash is equal to S into P. Then scaling matrix Sx is equal to S is equal to matrix Sx 0, 0, Sy. Here this one is scaled to this point. This enlarged. If the scaling factor is less than 1, it is moved towards the origin, then and the output will be smaller than the input. If the scaling factor is more than 1, greater than 1, then the output is bigger than the input object. Here it is. If the scale factors are in between 0 and 1, the point will be moved closer to the origin. The object will be smaller than the original one. Here the original one is P of coordinate 2, 5, and it is moved to P dash. Then it will be smaller than the original one. Here example P of 2, 5, Sx is equal to scaled factor Sx is equal to 0.5 and 0.5, that is less than 1. So the output is moved towards the origin and it will be in smaller size than the original one. If the scaling factors are larger than 1, the points will be moved away from the origin. The object will be larger. Here original one is P of 2, 5. Then we have used scaling factors as Sx 2 and Sy 2. Then it is moved away from the origin and it is also the point will be Sx 2 into 2 and 5 into 2. That is 4, 10. It is moved to the point 4, 10 and that one is enlarged one. And if the scaling factors are same, then Sx is equal to Sy, then that is uniform scaling. If Sx not is equal to Sy, the scaling factors are different, then that is differential scaling, that is change in size and shape. Here example, here square is converted to rectangle. Here we are using P as 1, 3 and scaling factors are Sx 2 and 5. Then the output object will be placed on at the point 2 and 15, this point. And general pivot point rotation. Here translate the object so that pivot position is moved to the coordinate origin. Here the triangle is here and the center is represented by this coordinate XR, Then this is one is original position and original object, and pivot point is this one. It is translated to the origin. Here pivot point is origin. Then rotation taking place. Rotation was about origin. After that, this rotated object translated to the original point, that is x or y. This operation is taking place in this case. And general fixed point is scaling also this one. This one is the original point xf, yf represented by this pivot point. Then it is translated to the origin. then scaling takes place. Here scaling factor is more than 1, so it is enlarged. Then next step is translate this scaled object to the pivot position. Then here are composite transformations, that is doing same operation more than once. If two successive translation vectors tx1 ty1 and ts2 ty2 are applied to a coordinate position p, point P, the final transformed location p dash is calculated as p dash is equal to t of translation of t of h2 y2 ty2 into the first thing is taking place here, that is t of th1 ty1 into p. First translated to this one and then translated among this one. So we can represent this here as t of ts2 ty2 into t of ts1 ty1 into p, where p and p dash are represented as homogeneous coordinate column vectors. We can verify this result by calculating the matrix product for the two associative grouping. Also, the composite transformation matrix for the sequence of transformation is matrix 10 tx2 0 1 ty2 0 0 1 into matrix 10 ts1 0 1 ty1 0 0 1 equal to here 1. Here it's 1. Matrix 1 0 ts1 plus ts2 0 1 ty1 plus ty2 0 0 1, or we can write this as t of ts2 ty1 ty2 into t of ts1 ty1 is equal to t of ts1 plus ts2 ty1 plus t2. That is, two successive translations are additive. Here successive rotations. Two successive rotations applied to a point P produce the transformed position as p dash is equal to r of theta 2 into r of theta 1 into p. This one is taking place first. So it is, we can write this as r of theta 2 into r of theta 1 into p. By multiplication, the two rotation matrices, we can verify that two successive rotations are additive. That is, r of theta 2 into r of theta 1 is equal to, we can write this as r of theta 1 plus theta 2. That is, first, if we rotate an object to an angle of 30 degree and next we rotate the same object to 45 degree, the ultimate result will be rotated by 75 degree. 45 plus 30, that is 75 degree. So that the final rotated coordinates can be calculated with the composite rotation matrix as p dash is equal to r of theta 1 plus theta 2 into p. Here successive scaling. Concatenating transformation matrices for two successive scaling operations produce the following composite scaling matrix. That is, scaling matrix is matrix sh2 0 0 0 sy2 0 0 0 1 into matrix sh1 0 0 0 sy1 0 0 0 1, which is equal to sh1 into sh2 0 0 0 sy1 into sy2 0 0 0 1. Or we can write as s of sh2 sy2 into s of sh1 sy1 is equal to s of sh1 into sh2 sy1 into sy2. The resulting matrix is the successive scaling operations are multiplicative. So we can write this as sh1 into sh2 sy1 into sy2. And other transformations are reflection. Reflection is the transformation which produces mirror image, that is 180 degree rotated image. Here original position is this one along the line y is equal to 0, that is x-axis, and is accomplished with the transformation matrix 1 0 0 0 minus 1 0 0 0 1. Here is the reflection along y-axis, that is line x is equal to 0, accomplished by the transformation matrix minus 1 0 0 0 1 0 0 0 1. And here there are four types of reflections: reflection about the x-axis, about the y-axis, about an axis perpendicular to xy plane, and passing through the origin. And next one is, last one is reflection about a line y is equal to x. Here this one is perpendicular to xy plane and passing through the coordinate origin. Here transformation matrix is minus 1 0 0 0 minus 1 0 0 0 1. And the